My thanks to Alan, Rick, and the Madison Gem and Mineral Club for having me, and I thank all of you for your attention. We have a lot to cover, as you can see up here. I'm not going to read that, but so please save your questions till the end so we can save a little bit of time. A little bit about me. You can read this if you want, but I'll just say that I can remember my first collecting trip of fossils at Estabrook Park with my sister in 1963, when some tough-looking kids approached us chanting, "Hector, Hector, rock collector." We were pretty scared, but eventually they apparently had enough fun and disappeared. I knew that I had reached a crossroad in my life at the tender age of 14. Should I avoid the path where I will forever encounter teasing of a segment of the population that will never know the tremendous joy and enlightenment that these dusty, old, inanimate objects can bring, or do I stay the course? I don't think I need to say which path I took. As you know, I recently wrote a book on the Milwaukee Formation with my friends Joanne Klusendorf, Don McCulloch, and Carl Brett. I'm going to start by mentioning what was known about the Milwaukee Formation prior to publication of our book. First, it was deposited in a sea that covered Milwaukee, Wisconsin in Middle Devonian times around 385 million years ago, and that it lies between the Upper Devonian Antrim Shale and the Middle Devonian Thiensville Formation. It has many species in common with some of these formations of the Cedar Valley group in Iowa. We also knew that it preserves fossils of many invertebrates as well as land plants known as lipopods, and one of the most diverse Devonian fish faunas in North America. And we were aware that its fossils are preserved in many different ways, and that many fossils are geodized with sulfide minerals in many of them. We also knew that a lot of its fossils preserve color patterns, and that others are exceptionally preserved. One fish tooth, for example, preserves carbonized pulp in its pulp chamber. Finally, we also knew that certain trilobite fossils of the Milwaukee Formation were used by Eldridge and Gould to support their famous theory of punctuated equilibria. Then Don, Joanne, Carl, and I took a closer look and brought things a little more up to date. Here are some of the things that our book shows about the Milwaukee Formation that were not previously published. First, we now know that it's more diverse than we thought, with about 250 species, from around 100 families, at least 16 phyla, and 4 kingdoms. Its biota includes cladoxylopsids. There'll be a lot of big words here, but I'll show you what they mean. Cladoxylopsids was a type of tree that lived around that time, that first started out about that time. We also found its biota includes a giant fungus called Prototaxides, the height of a 2-story building. It also includes edroasteroids, raniform placoderms, and 3 genera of graptolites. Again, I'll show all of these later on. Also, we now know that many of its animal groups, such as its trilobites and blastoids, have more genera and species than previously thought, and it has more ichnogenera, also called trace fossils, than previously published. The book also updates the biological placement of various groups of organisms, too many to mention here. And it's the first book to show apparent brooding chambers in one of the Milwaukee Formation's bryozoans, and the first to show certain anatomical details for some of its crinoid species and other taxa. And finally, it's the first book to present a detailed account of Milwaukee's natural cement industry, without which the majority of the fossils would never have been collected. There would be no book, and I wouldn't be standing up here talking to you right now. So with that introduction, let's take a look at some pictures. First, this is a side view or a cross-section of about 3 feet of the Milwaukee Formation at its type locality at Estabrook Park. As you can see, there's a plane of contact right here where this vegetation line is. That is a disconformity. Below that is the Berthollet member, which has more or less molds as preservation. It's more heavily bedded, dolomitic, whereas above this conformity here, you have a little bit of the lindworm member, which is shalier, and the fossils are preserved in the form of permineralization mostly. You can see these black voids that were here, little cavities that were filled with black substance. Actually, it's asphalt. These are asphalt vugs that sort of demark, you know you're in the top layer of the Berthollet member if you get that. When the sea receded here, there was a little non-deposition, a little erosion, so the Berthollet was above sea level. And when it came back, sometime later, we're not sure exactly how much, certainly less than 1 million years, about the same animals came back with it. Little different proportions of the animals, but about the same species came back. The sediment was quite different, though. Like I mentioned, it's more thinly bedded and shaly. Preservation is different. This goes down, Berthollet member goes down about 20 feet. Lindworm goes up about 20 feet, and then kind of blends in with another member called the North Point member, and that's very similar to the lindworm. Now we'll talk a little bit more about taphonomy or preservation. Lots of kinds of preservation, as I mentioned, were found here in the Milwaukee Formation. The first being permineralization, where you get the hard parts, the skeletal materials, carried over, and all the little pores that are inside of that skeletal material, maybe not all, but get filled with another mineral, such as calcite. And they get in there by way of the groundwater, which of course has the dissolved minerals in it. And these are some examples of permineralized fossils from the lindworm member in this case. These are lindworm member. You can also get apatitic skeletal materials like these here. They look a little different. They're permineralized a little bit, but they're a different composition. They're made of calcium phosphate or calcium fluorophosphate, also called apatite. And you can see, this condylaria, the fish tooth. Fish fin spine. These are called the brachiopods, and this is a fish dermal plate or naphal plate. And you also get a lot of carbonization. Here I show 3 different kingdoms. This is a plant, this is an animal, graptolite, and this is a fungus. These are all 3 different kingdoms of organisms that are fossilized by carbonization. Where you don't have any biomineralized materials in the skeletal materials, there's just something like wood or chitin, something like that. And those typically tend to form by carbonization, or fossilized by carbonization, or frequently, not always. So that's another one. Then we also get replacement. A lot of fossils are replaced. This is one species of clam, or bivalve, that are all fossilized by one kind of replacement or another, where you have a replacement of the skeletal material by another material, another mineral. In this case, we have, this is all 3 of these colorful ones here were originally marcasite. And marcasite, of course, when it gets in contact with water or moisture, it tends to change. It tends to change into ferrous sulfate, and if there are other impurities in there, you get other colors like that. So it's kind of pretty. The white one up here is replaced by silica, specifically chert. So these are very common. This is a very common thing in all 3 of the members of the formation. We also get internal and external molds. I mentioned Berthollet member is mostly internal molds, where the inside of the organism deteriorates away, rots away, is eaten away, whatever, leaving a cavity. And the cavity is filled with sediment. The sediment lithifies, turns into rock, and that's your internal mold. That's what you see on the, whoops, that's what you see on the left side. Oops. The fossils on the right are permineralized fossils of the same species to their left. So this top one here is a brachiopod. If you chip away this shell on this brachiopod, you get that internal mold underneath. So you see a lot of different details in there because that they're not shown on the outside because you don't see them on the outside. Those are the structures, like in this case, those are hinge structures that are inside of the shell. And there's a trilobite head, same thing. You get stuff here that you don't get any filling in the interior of the trilobite head, like tubercles, facets from eyes, things like that. And so on with the snail down here. was also a lot of geodization. As I mentioned earlier to somebody, I kind of wish there wasn't so much geodization because I'm not a geo guy. But there are lots of minerals inside of some of them. And I have to say, I keep them if I find them. Although you're not supposed to keep fossils from Essex Park anymore, which I don't. But these are all calcite geodes. And of course, geodes, we know that's another cavity that's lined with some mineral. In this case, these are calcite geodes. So calcite lines the cavity on the inside of the area where the animal's insides used to be. The three, or two of these here, these two are geodized brachiopods. This is a geodized cephalopod. It's got some pyrite in there also. And this is a geodized bryozoan, I think. And it's got some millerite or nickel sulfide inside. So these are all sulfide minerals that, of course, probably crystallized before the calcite did. The calcite is seen forming around the other minerals. So much for minerals. We also get, well, I guess you could call this is another mineral too, asphalt deposition. I mentioned that before. This is a closer view of some of those asphalt voids and vugs, they're called. And this is an asphalt that's coating the internal mold of the brachiopod here. So we get a lot of that in the Berthollet member at the top. Then I mentioned the color patterns. It's fairly uncommon, not real rare, but fairly uncommon to find color patterns. Of course, these aren't the actual colors that the animals had, but these are the patterns that you could actually see in the outside of the carved part. This one on the left here is a fish fin spine from a placoderm. It's a spine like you can see, like a lot of fish have now. It's almost like the mast of a sail, pulling the sail up and holding it in place. That mast is the spine. And these two on the right here, up here, are brachiopods, and this is a triloid pygidium, which has the middle part, the axial lobe, has some indications of color patterns on that as well. The rock formation also has a lot of depth assemblages like these. And sometimes, I think I've heard one person make a sound because sometimes people think they really like these things. I mean, I kind of like them too. In fact, this one here, oops, this one here, what am I doing here? This one on the right, it has about 17, at least 17 species of things that I can see on it. The one on the left has almost as many. Brachiopods, bryozoans, tentaculitoids, heterelloids, you name it, it's got them on there. My son Kevin back there, the one who was talking before, is the one who found that one, by the way. And these are from storm deposits. So when the storm came through and kind of scoured the bottom of the shallow sea that this was in, it busted up all the pieces of skeletal materials and jumbled them up in a heap, buried them, fossilized them, and here they are. Storm deposits. Now we're going to talk a little bit about the life in the Devonian Milwaukee. The Devonian was a very special period because it really brought out the last of the big phyla that hadn't come around yet. And they were still there because we didn't have the end of Permian extinction yet. So nothing really big became extinct. There was some extinction before in the Ordovician stuff, but not really tremendous ones. So we had the very first fish with jaws in the Devonian. We had the very first trees, the very first forests. We have fossils of all those in the Milwaukee Formation. We also have all the major marine modes of life represented, organisms that swam, crawled, dug beneath the sediment, or attached to the substrate or to other organisms. There were predators, filter feeders, suspension feeders, scavengers, and grazers. There were even terrestrial organisms, as I mentioned, that washed to the sea, settled at the bottom, and preserved as fossils. And there were a lot of organism interactions, which is sort of the same symbiosis, the relationship of one organism to another species. In this case here, these are the special kind of symbiosis called commensalism, where you have one animal basically living on another species. In fact, these are actually attached to, for the rest of their lives, these different shells. They're encrusters. And you're going to hear me use the word encrusters for the next however long I've got. The one at the top is a coral encrusting a brachiopod. This is a heterelloid encrusting a brachiopod. This is brachiopods encrusting a clam. This is an asteroid encrusting a brachiopod. And these are microconchates encrusting a cephalopod. And you get any other combination you can think of. You can pick up a rock in the Milwaukee Formation And I almost dare you not to find some other organism encrusting it, or having encrusting it, with some kind of an outline of it. Now we're going to go down to different phyla. I mentioned a lot of phyla, so this can take some time. I'm going to try to rush through some of this stuff. The first one was protist. This is actually a whole kingdom. The protist is a kingdom. And we have the radiolarians and the foraminifers represented in the Milwaukee Formation. There were other kinds of protists. Protists are one-celled organisms and sponges. Radiolarians really didn't preserve very well. They're harder to see. They're probably a lot more than we think, but they were so small. And I don't have any good photographs of them. They had a siliceous skeleton made of silica. That's about all I'm going to say about the radiolarians. The foraminifers, there are a lot more of those. They're a little bit bigger. They're again single-celled organisms. They usually have a shell on the outside. And the specific kinds that we have here in the Milwaukee Formation were the agglutinated foraminifers. And these are called that because they didn't have a test that they secreted. They didn't have a shell that they secreted. They stuck little particles that are sticky outside. And that's what you're seeing. These are 10 different species of foraminifers, agglutinated foraminifers. And that scale bar up there is 0.2 of millimeters. So you can see how tiny these things were. Most people have never, they found them, but they never even knew they did. Because they're so small, and it looks like junk you want to just clean off of the fossil, you know. But these are actual animals. So much for that one kingdom. One kingdom down, 3 to go. That's the littlest one. Here get the animals here. This is the biggest one. First phylum we're going to talk about is the cnidarians. Includes corals, the jellyfish, the hydras, things like that. All we had in the Milwaukee Formation were the conulariids, the rugose corals, and the tabulate corals. As you can see, the conulariids were now considered to be cyphozoans, which is a type of jellyfish. And they look kind of like this. They were a little bit unusual as a jellyfish goes because they attached themselves. There were showed 2 of them attached to a floating log. And we see these ribs going across they had. And they had sort of a 4-fold symmetry, 4 different sides to the pyramid. These are 2 of the sides here. Here's some more fossils of these. This is called Condylarea milwaukeeensis. It's also found in Iowa. And they don't look real pretty because they're very soft, as I mentioned, phosphatic. They're very thin outside skin rather than a shell. Very flexible, almost like a skin, called a periderm. So it doesn't fossilize very well. In fact, these are about as good as you're going to get for the Milwaukee Formation. In fact, some of these are figured specimens. This is a holotype right here, so you can imagine. Anyway, that's the first kind of cnidarian. Second one is rugose corals. You can see here, these are solitary rugose corals. They have to be colonial also, like the Petoskey stone, which polishes up real nice. Those are colonial rugose corals. These are solitary. And if they look a little bit like a sea anemone, anybody who's ever been to a tide pool or whatever, it's because they were related to sea anemones. They're both anthozoans. Except that instead of being squishy all the way around, these are made out of coral. These are made out of calcium carbonate, this brown part down here. And the soft animal, the soft polyp on the side, on the top here, if you would happen to pull that out, they're extinct now, but if you would have happened to pull one out of there, there'd be a little cavity there called a cup. Sometimes these are called cup corals, in fact, because of that. If you fill a cup with mud, the mud turns to rock, you get this. So this really is the filling of a cup of rugose coral, rather than being rugose coral. You do get, in the Milwaukee Formation, in the Lindworm member, you do get actual permineralized rugose corals. I just don't have any photographs here to show you. The other kind, and here's some more examples. The other kind of coral, and the last cnidarian, is the tabulate corals. And all tabulate corals are colonial. They're kind of similar to rugose corals, but they're colonial. They have these little tabulae, as the name mentions, little tails that they have as the animal goes up the tube in which it lives. And you can see, again, this is the same one I showed before. It's encrusting. And most of the corals in the Milwaukee Formation were encrusters. I promised you I was going to use that word a lot, and this is another one of those encrusters, just like the foraminifers are. And we had lots of species of these actually, but none of them formed a reef. So there were no reefs in the Milwaukee Formation. I've seen a couple of people that kind of drew reconstructions way back a long time ago that had these big reefs and stuff. There were no reefs in the Milwaukee Formation. There were reefs in other formations in other parts of the world, but not here in Milwaukee. It just doesn't. A reef has to have a very distinctive, definite structure, and there was no structure like that in the Milwaukee Formation. But there were a lot of corals encrusting different things, and a couple of them like these, it kind of rose up above the thing that was encrusting, and then there was this one here which is encrusting a cephalopod. This is another holotype. If you see stickers like this, it means it's probably a special fossil, like this is a holotype, or some other type, like if it's a diamond, it's usually a different kind of a type, or a figured specimen in some book that was written before I wrote mine, or some other publication. And these are tentaculitoids. This is another phylum. These are something called a lophophorate, an animal that had a lophophore, which was a food gathering organ that had cilia around the mouth, and it could withdraw the whole lophophore into the tube in which it lived and put it back out again. Corals had little tentacles, but they didn't have a lophophore. And these are solitary animals. These particular ones here were, well, all of the, as far as we know, all of the tentaculitoids were solitary, but these particular ones were free. They weren't encrusting anything. They're kind of cone-shaped, maybe ½ an inch long. These are pretty common in the Milwaukee Formation. But they weren't all like this. They could be coiled like this, and they could be encrusting again, like these are. You see two different species. These are called microconchid tentaculitoids. There will be a quiz at the end. You have to know 90% of these. These are two different species on this bryozoan up here. And here is a brachiopod encrusting cephalopod and encrusting a different kind of a cephalopod. So those are microconchids, and that's all I'll say about that. Another kind of lophophorate are the bryozoans, a lot more common. Bryozoans are very common. Most of them are calcareous. You know, they're all colonial, and most of them have a nice skeleton like this. Look a little bit coralish, but they're not. They have a lophophore, as I mentioned. Corals didn't. And they also have a lot of polymorphism. This looks a little bit like a beehive. It's almost like kind of how it was, really, because in each one of these holes there was an animal. And if you have two different kinds of holes or apertures, that means there are two different kinds of morphs. One for maybe feeding, one for reproduction, one for defense, something like that. Some of them have like 5 or 6 or 7 different morphs. And you can diagnose them by looking at the patterns of these holes, basically. And here's one of them that has one of these morphs. My son Damien found this one. This one is the only one that we know of that's like this. In fact, there's a bryozoan specialist that wants this. He wants to do a thin section in the tubercles. This is small. This is really small. That's a destructive test, so my son Damien said, forget it. But anyway, these little blistery things, these little subspherical things, those are like egg cases called brooding chambers. And they're sort of outgrowths from a certain morph of the bryozoan. That's for reproduction. This whole thing is only about 3/4 of an inch high here, so it's very small. And then you get lots of different kinds of bryozoans. I'm just going to pan through most of these things. You're going to see just a flash, like flipping through a book. One kind, this is called Lichenalia. I'll show you this one later on too, Lichenalia. I used to think this was a stromatolite too, until we did our modern analysis of it here. This is the same kind of bryozoan again. One of the most common species that you'll find in the Milwaukee Formation is this one right here. Nice, large, massive bryozoan. This shows nicely the distinctions between, these are close-ups of here, closer to that, closer to that, etc. Showing the different patterns, so that means that they're different species. You look at the whole colony, and they look pretty much the same. You really can't identify them that way. You have to look at the structure. Sometimes you have to actually do a thin section inside to identify them, but unfortunately the fossils in the Milwaukee Formation don't have the insides. They're usually geodized, or they're recrystallized, or just gone. So fortunately, a lot of them are identifiable by the outside features. Here's another one that's kind of fan-shaped on the left, kind of branching ramos on the right. Then we get to a different kind of lophophorate phylum, heterelloids. These used to be considered bryozoans, but they're encrusters and they're different. These two are encrusting, they're again lophophorates, but At least we think they are. They're extinct now, but they are some evidence, fossil evidence of lophophores on these things. These two are encrusting brachiopods. These two species are encrusting cephalopods. And we have the brachiopods. The biggest, in fact, the Devonian is the age of the brachiopods. You've seen probably more of these than almost anything else from the Carboniferous, I mean from the Paleozoic era around here. It looks a little bit clammish, you know, two shells, but of course the symmetry is completely different. If you take a clam and lay it out this way, the opening facing in like this, the symmetry would be across here, where this shell will be a mirror image of this shell. Now, obviously that's not the case with brachiopods here. The symmetry would be down here. The left would be the same as the mirror image of the right. So the brachiopods, there were about 48 species of brachiopods in the Milwaukee Formation. More than that, I'm sure, we need to do more work on it and really sort out what we've got. But at least 48, and I'm just going to pan through most of them. But I just want to show there are 3 different kinds of brachiopods. The linguliform brachiopods is the first one. Linguliform meaning tongue-shaped because they kind of look like the shape of a tongue, some of them. They're phosphatic, so they're different looking color and sheen and whatever. And they don't have a hinge. So they're less like a clam than a clam is, because the clams have a pretty nice hinge typically, and some brachiopods also. Then there are the craniiform brachiopods, and these are encrusters again. All of them are encrusters. They fuse themselves to other shells for their whole life after they grew up out of their larval stage. And they're still alive today. All of these 3 main classes of brachiopods are still alive today. They're all marine. Some brackish, but mostly marine. And these 3 are encrusting a cephalopod in this case here. Then we get the biggest group of brachiopods, a Rhynchonelliform, and this one here, I'm just going to go bam, 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 because I'm showing you a lot of these, and I don't have time to stop and look at these things. Take a good look or buy the book. It's one or the other. Take a look and buy the book. Okay. We will get to the end eventually here. Brachiopods are nice, but okay. Hyolids, that's our last lophophorate. The lophophorates, of course, we all know what that is and have lophophore. Some fossils actually have one preserved, and that's how we know. Before then, somebody thought they were chimularians, like that very first cyphozoan that I showed you. Except that these don't have the ridges going around across them. They don't have the 4-fold symmetry, you know, like a pyramid with 4 sides. And they're hyolids. They became extinct, like a lot of these other things, at the end of the Paleozoic. Whatever happened to wipe out 95% of all the animals at the end of the Paleozoic. These went along with them. Mollusks. One of the biggest, most important groups of invertebrates. Of course, includes the clams, the snails, the octopus. There were no octopi yet. They didn't come about until the next period. But we did have the snails, or gastropods, rostral conches, bivalves, or clams, and cephalopods, which includes the octopi and squids. So first we're going to look at the gastropods, or snails. They're snails. Nothing really fancy to look. We all know what a snail looks like. That one shell, at least all the ones in Milwaukee did. Different kinds, pretty many different species. Nothing too spectacular. A lot of variety. The high spire ones like this. Then we had something called the rostral conches. Only a couple of species of these from the Milwaukee Formation. This kind of mollusk used to be classified as clam, but then they thought, well, all the studies that they did showed that if you were to take, it had 2 shells, but if you were to take and open or close the shells, you'd probably kill the animal because they were not decalcified along the hinge line. You really can't even call it a hinge line, but you know, did they maybe evolve into clams? We don't know. But anyway, you can hardly tell 3 views of the same fossil. It's hard to say what that is because their symmetry is so wacko. Small group. Okay, now we have the bivalves. Lots of species of bivalves, or clams, in the Milwaukee Formation. Almost as many as there are brachiopods in the Milwaukee Formation. So again, take a good look. There aren't quite as many of these that I have pictures of here. As you can see, these are, if these things look like mussels, they are. These are mussels, and if you're getting hungry for seafood, how about scallops? Okay, we had those too. If you take that shell and turn it upside down, it's the shell from Shell Gasoline, which you've all seen their logo. A lot of different kinds of bivalves. One in particular I want to show you right here. This one, you can see a little hole there. What do you think that might be? Anybody?
Snail eating.
Yes. Either snail or, we're not really sure if it's a snail, probably was a snail, or a worm of some sort. Drilled a hole, reached inside, ate the animal, and then went about its business. Which is actually pretty uncommon for Devonian clams, actually. As my co-author Carl Brett said, it's actually pretty rare to find that. That kind of behavior, the kind of animals that did that usually didn't get a good going until a few million years later. And then we get the last group of mollusks, the cephalopods, which of course, this guy looks a little bit like a squid or octopus. That's because we're all talking about cephalopods. There were three major kinds of cephalopods living in the Milwaukee Formation. We have some of those living today, the nautiloids, the chambered nautilus, pearly nautilus, and it's a nice coiled shell. Looks a little bit like this one, sort of, but a little more colorful. That's actually an ammonoid, actually, but these are all nautiloids, very closely related to the living nautilus. Different shapes, different, you know, you can see that there's some ornamentation, different shapes. Swimming usually, this is kind of conjectural. We don't know if they really swam this way, but they might not have swum at all. This is a very large one here, actually, a very large species. The Milwaukee Formation had a lot of different species, more than most places, of Devonian cephalopods. Very, very prolific and very, very diverse. So let's look at the nautiloids first. These are some typical fossils of nautiloid cephalopods, like the different shapes. These are casts showing a reconstruction of what the shell looked like before they were compressed, because most of them get distorted pretty badly from compaction. But this is what they look like on the right here when they were freshly dead. This is more fossils, different ones, different species, different genera, some coiled one, some straight-shelled ones, orthocones. And then we got to mention there were a third kind, the actinoceratoids. And the one on the right is an actinoceratoid. See what nautiloid on the left, they don't look very different from each other. You really can't tell from the outside. You have to go inside the shell to tell, which this doesn't show. They have a siphuncle. All the nautiloids and actinoceratoids and ammonoids and a few other subclasses have a chambered shell with a siphuncle going through and septa that separate the chambers. And the siphuncle of the actinoceratoids is really weird looking. It's really lumpy looking. And you can't see that here, but anyway. So much for the nautiloids. Now the actinoceratoids. Now the ammonoids, very rare. Now you're all used to seeing, those of you, some of us more than others, have seen lots and lots of ammonoid fossils. You've all seen them. You've all seen them. They're really pretty, like mother of pearl, color on them, really beautiful, intricate sutures on the outsides of the shells. That was later ammonoids. They were just starting out in the Devonian. They were not really pretty yet. Plus, of course, mother of pearl or aragonite doesn't last very long. It's not very stable. And this is going way back to the Devonian, folks, so it's turned to calcite by this time. Also, these are internal molds, so you wouldn't find one anyway, find a shell anyway. But anyway, they were very rare. These are the only two fossils I've ever personally seen. This one here is was identified by James Hall himself. His label, his handwriting is on there, calling it goniatides. I'm not going to call it goniatides because I'm sure it's been split many times. This could be any one of a number of genera. But it's an ammonoid anyway. This one here, this artist, Cleland, really used his imagination to do this drawing because he got this out of this. If it weren't for this, I would just throw this thing away, probably. I wouldn't know what that was. But somebody was right, because as it turns out, there are ammonoids in the Milwaukee Formation. Okay, now we get to another phylum, the annelid worms. These are the segmented worms, like your regular old earthworms, nightcrawlers, leeches, things like that. There were certain kinds of annelid worms called polychaetes, and they had jaws. And the jaws are called scolecodonts. This is a scolecodont. Again, this is about 0.2 of a millimeter, so it's very small. Easily overlooked. And this is the best photograph I've got of this thing. But because we know that there are spelegodonts there, we know there were annelid worms. And so when I show you the trace fossils later on of these squiggle things, these trails in the rocks, some of those were probably made by annelid worms because we know they were present. Now we get to the phylum, the Arthropoda, which is the most species-rich phylum in the world. Probably ever was, at least since the Phanerozoic, at least. And we had two major groups of arthropods. Of course, arthropods are segmented and they have jointed legs. Okay. The arthropods in the Milwaukee Formation were the trilobites and the crustaceans. And I'll show you the trilobites first, and then I'll show you the crustaceans. There were two main kinds of trilobites in the Milwaukee Formation. But all trilobites had their body divided up into 3 lobes, like this, of course, middle lobe and 1 lobe on each side. And they grew by molting, like any arthropods of today do. So most of the fossils that you find are molts. They're pieces. This head or cephalon broke off. This free cheek broke off right around in here. Here's a rolled up in ball, a complete one, which you find a lot of that activity in trilobites, trilobite fossils. This is that same fossil, 5 different views of it. It's called Eldredgeops, normanensis. Talked to a lot of trilobite authorities to get that, including Eldredge himself and other people. Eldredge is the one who told me to put the question mark in there, by the way, just in case you're interested. And here's some more. You can see some nice eye facets on this one here. These are more typical of the kinds that you'd find because they're, you really don't find very many complete trilobites in the Milwaukee Formation. And then these here are some more partially enrolled ones. And now you get one fossil that shows the pygidium or tail from the 2 different major kinds of trilobites in the Milwaukee Formation. The one on top is the same one you were just looking at. On the bottom is a proetid. This is a phacopoid. This is a proetid. The proetids have a flattened border along their back. You don't have that on the phacopods. At least proetids in the Milwaukee Formation had a flattened border back. Not all of them did, but the ones here did. So, a lot of work needs to be done on the trilobites. You can see the border much better on this one here. My wife found this one here. Probably the best proetid I ever found in Wisconsin, in the Devonian. And then these are all molts from various other proetids. A lot of work needs to be done on these. All we know is like there are several genera here. These are probably Decanella. This is probably Pseudodecanella. This is probably Crassoproetus. I don't know what the heck the rest of these things are. This one is really weird. These are kind of undiagnosable. There's nothing up there to see what they are. A lot of work needs to be done on those. And then the other kinds of arthropods, the crustaceans, as I mentioned, well, there were 2 different kinds, if you'd seen that first slide, the ostracods and the phyllocarids. The ostracods were really abundant. There are a lot of them. There are 15 different genera of ostracods in the Milwaukee Formation, and I haven't got a single good photograph because they need to be prepared. So anybody who is looking for going back to grad school or whatever and doing their PhD, you've got thousands of specimens to clean off and find out what the heck we've got. Not just ostracods, but everything else too. But the ostracods, it's pitiful. We know that there's enough to say, okay, this thing is really dirty, but I know this is such an Ulrichia or something like that. Anyway, but they're small bivalve arthropods. Like I said, no pictures. This is a bigger bivalve arthropod called a phyllacarid, and part of its body extends back beyond the shell here and ends, in most cases, in a 3-pronged tail like that. And there's another genus of this as well from the Milwaukee Formation, which I don't have photographs of either. So that's the phyllacarid. So that's the end of the arthropods. Now we get the echinoderms, meaning spiny skin, of course, because inside their skin, they have little pieces of calcite, perfect calcite crystals embedded in the skin. Starfish. The texture of starfish, ever picked one up, or you've seen maybe dried ones in an aquarium or something. That's an echinoderm. But one of the neatest things to me about it is that all echinoderms have a water vascular system. No other phylum has a water vascular system. And what that is, it's like a hydraulics system. So if you open up, if you lift up and turn upside down a starfish, you see all these little tiny hundreds of tube feet underneath wailing around. That's what moves them around and sticks them to the rocks. And those are tube feet, part of the water vascular system of that starfish. We didn't have any starfish in the Milwaukee Formation yet. We cleaned all that stuff out. Who knows what we're going to find, but we do have crinoids, blastoids, and edroasteroids. So here are the crinoids. We have lots of different species of these things, and a lot of work needs to be done on them. But of course, a crinoid doesn't have like the 5 arms, 5 legs like a starfish has. It's got 5 arms instead, or multiple of 5 arms. And they're up there, like looks like a flower, up there in what looks like the bulb of the flower, the head. That's where the arms are. Those things look like petals of the flower or the 5 arms. And almost all trilobites had 5 arms or multiples of 5. And at the other end, they attached, or not permanently necessarily, but they had a hold fast at the other end and kind of anchored down and stuck to some object. And lots of different kinds of these things. And again, it was 5. Like starfish had multiples of 5 arms or legs. These have 5 arms. They could have 5 something else, like some of these other things do. But first, these are the crinoids. This crinoid stem here, or stalk on the left. And this is a piece of the stalk broken off from right here, which is the hold fast, holding it fast onto this shell. And here I have photographs of a couple of different heads or calyces of a crinoid, but the piece of one of the arms associated with its calyx right here. Some more species of calyces, of crinoids, more. And we have a nice close-up of 2 arms of a crinoid with some more detail that I wasn't showing in the other photographs. This was found in the glacial drift, but we're pretty sure it's Milwaukee Formation stuff. It was found right in Milwaukee on Teutonia Avenue. And these are some comparisons of a piece of an arm from 3 different species of the same genus of crinoid. For comparison's sake, you can see they're all different. None of this was known before we wrote the book because the arms of these species were not even known except for one. This is the head of another species of crinoid. This is Taxocrinus telleri. There's a specimen of this, I believe it's still on display here in the museum. And it has, this is the whole crown actually. The calyx down here with all 5 arms together is the whole crown. There's more specimens of that same species. Now we get the blastoids. They're kind of like crinoids, but they don't have any arms. They do have something that's not shown on here, though, because it was too hard to depict on an oil drawing, which this is. And that was little brachioles. So you have, remember, no arms, but there are 5 ambulacra. 1, 2, 3, 4, 5. And along each ambulacrum is a whole series of these little things called brachioles coming off here that were also for food gathering. It was just too hard to show on here, so we left them on. Lots of different kinds of blastoids again, you know, lots of different kinds, different genera, different species. A lot of work again. Somebody's going to have a lot of fun with this. Edroasteroids. It's the last echinoderm group, and these didn't have a stem or stalk at all. These were, again, encrusters, and they were encrusting brachiopods. This kind of edroasteroid, all the fossils from the Milwaukee Formation are found in the same kind of brachiopod. They really like that kind of brachiopod called Devonatropod. And they didn't have arms, they didn't have brachioles, they didn't have, all they had was 5 ambulacra. So this thing looks like a meatball with onions. Those onions are the ambulacra. You notice there's 5 of them. You can see on this fossil down here, you can see some of the ambulacra on it here. They usually disintegrate and it just becomes a bunch of dissociated plates, like these here. This is just almost an outline. It's just a jumble of plates. This is a nice outline of the plates, characteristic look. Okay, and those weren't known from Milwaukee before he wrote the book. Nobody ever published anything on it. The same thing with these, the graptolites. This is the phylum Hemichordata, the one right before our own phylum, the Chordata. Only they're colonial and marine. And the kinds that we had in Milwaukee, these graptolites, are called dendroid graptolites because of the shape of the net. And they were attached. All the graptolites were attached. And the dendroids looked like a net hanging down, like we've got these showing here hanging down from a floating log again. 3 different genera at least that we have that we know. I won't give you their names right now, I don't want to too much. And then we get to our own phylum, the Chordata. We had 2 different kinds of chordates in the Milwaukee Formation. We had the conodons, of which you're looking at some of their conodon elements. And then we had fish, if there is such a thing. Okay. But the conodons were about a couple of inches long. The animal just looked kind of worm-like, and it had these little conodon elements in its head. And sometimes it could have a whole bunch of different kinds of these things. So even though these things are given different names, these are 20 different names of conodon elements right here. They're really not from different species necessarily. We might have only represented maybe 4 or 5 species right here because there are several different kinds in one animal. But anyway, we had 20, at least 20. There's more work that's been done. It's not published yet, so I couldn't show any of that out here. Then we get, and by the way, some people consider them to be actual vertebrates, but they don't have a cranium. There's no evidence of a cranium on these. So we usually keep them in a separate group of chordates along parallel with the chordate, with the vertebrates. Now we have the vertebrates themselves. And I mentioned they're all fish of one kind or another, if there is such a thing as a fish. You will not find any more in most textbooks or any other books written that's scientific will use the word fish anymore, unless it's in the colloquial. It's like Pisces. Bye-bye Pisces, you're gone, okay? Because of complex things. Get the book, and I've described it in there exactly what I'm talking about. Too long. Okay, the first kind of, I'll use the word fish because it's not scientific. I can use any word I want. You know. I'll call it a fish, okay? Because it looks like a fish. Everybody else is thinking it's a fish when you look at it. You're going to say it's a fish. The placoderms have bony plates on the outsides of the body. And most of you have seen pictures of these things. I'm going to show you. It's like a mosaic going in the outside of the front half of their body, their head and trunk region, like a jigsaw puzzle. And there were several different kinds. The one that we think of most and the most species-rich kind of placoderm was the arthrodires. And the arthrodires look like this. These are the killers. They included the killers, the big guys. And you've all seen these in museums and pictures. This one here, Joanne Klusendorf, our co-author, is sitting in front of this one here. This happens to be a cast of something from Ohio. And you can see the one here from Milwaukee is virtually identical. Well, very similar. It's a different genus, but it's very, very similar. And about the same size, about the size of a great white shark. And every bit as deadly, we think. I mean, with teeth like that, I mean, what else would they use them for, you know? I can imagine this thing's bitten off the heads of a lot of sharks, because the sharks were a lot smaller than these guys in those days. Okay, so I'm going to show you just a couple of things here. These are all different names for all the different kinds of bony plates that are in this jigsaw puzzle. This one down here is an IG plate, or infragnathal, or lower jaw, which may or may not be homologous with our own jaw. It's debatable. But anyway, we know what it was used for. I think it's pretty safe to say it was used for biting, chewing, things like that. Biting off heads of fish and things like that, and chewing them. And this one here is another tooth plate for the same way that you would use a tooth. And this plate here is called the ADL plate, I believe. Yeah. And the reason I'm showing you those, I'm going to show you their fossils right now. This is the ADL plate. This is the holotype, actually. It's called East Monosteus pustulosus. That's also on your test. Okay. And that's just one of the plates in the mosaic, but it happens to be the holotype, and it has bumps that are called pustulosus. And it's an important species, a very important fossil, believe it or not. This is the lower jaw. You can see the beautiful shearing edge here. You can just imagine, you know, how dangerous that thing would have been. Again, this thing could be as large as a very large great white shark. Right in Milwaukee, right there. It's a reconstruction of the bottom. If you can see it, you can see they've reconstructed the front and back end of it, a little bit more. And this one on the right here is that upper tooth area, that upper jaw part. Some more. And this one here, I want to show you this one here. This is actually even bigger than that one. This one is called Titanichthys. This is a piece of one of them. And when they get that big, you're not going to find the whole thing. You're going to find just bones, pieces. But some places, these things are like, you find a jigsaw puzzle that drops on the floor and just some chunks that have pieces together. You can kind of put them together. That's what they did. But this is a plate from Titanichthys, which was not dangerous, hardly at all, unless you happen to be plankton. It was the size and probably had the lifestyle of a basking shark. So it was a filter feeder. And very harmless, very big, very cool, I think. There were also lots of fin spines. I mentioned all the four groups of fish, all the main four groups of fish in the Milwaukee Formation had fin spines. These fin spines are probably from arthrodires. We're not positive, but we think they were. And they might have been from Tictodonts, which I'll show in a little while, because they were never found directly associated. Some of these things, some layers are they're all over the place. But it's hard to associate them sometimes. But anyway, it's a different kind of fin spine from the other ones. This here I'm showing you because it's, what the heck is that? It's just a rock, right? People that have studied this is a famous fossil. This shows bite marks, tooth marks on it from probably more aggressive, bigger arthrodire chewing on another one right here. I didn't say that. That's what all the other specialists, and I don't hear anybody debate that. This is a Tictodont. This is the next kind of arthrodire. We have placoderm. Tictodonts were smaller, and they weren't ferocious at all. They probably were chewing and eating brachiopods, things like that, sort of like a shell-crushing shark. They had these teeth, or tooth-like, dermal plates that had like a rat-tail file up here, which is really what it reminds me of. Great for crushing and grinding shells. Like if you're a brachiopod, I'd try to stay away. And that's about, most of the fossils are of these naphal plates or jaw plates. Another species, more species. These are scales. These are scales from Tictodonts. They had scales. And here's some fin spines that we know are from Tictodonts, because they've been associated with actual Tictodont jawbones. You can see a little different ornamentation on there. Some more species of Tictodont fin spines, some more plates. Now we get to the rhenaniform placoderms. Rhenaniforms were ray-like. I think I mentioned at the very beginning of my talk that this is the first time we mentioned that there were rhenaniform placoderms in the Milwaukee Formation. What's the big deal about that? That's the one that I've got a fossil of that in that little black box right over there. You just need a little tiny piece of it to know what you've got, because their tubercles are shaped like stars. If you enlarge that, this whole thing is about a ½ inch long. You enlarge that, they're shaped like stars. It's called an asterosteus, which is a type of rhenaniform. Ray-like, like stingray, stingray, manta ray, flat, broad body, bottom feeding. That's the kind of fish that this was. And then there were petalichthiiforms. Those were bottom feeders also. I don't have any other pictures of these. And there was another kind of placoderm. Now we get to the second kind of the four kinds of fish. This is the chondrichthyes, which are the sharks, rays, chimeras. And they have a cartilaginous endoskeleton. No bones as such, they've got a skeleton made of cartilage. And yes, we had sharks in the Milwaukee Formation. There were sharks, as I mentioned. I'm sure they were food of a lot of the big arthrodires. They were kind of basic looking. They were pretty small. There were a lot of different kinds of them. They were just starting out. They had jaws. The first jaws to appear were in the Devonian, so this was when they started out. And unfortunately, we didn't have very many fossils from these. There was a nice tooth from one that was an inch wide that was published in 1911, but it's missing. Nobody knows what happened to it. And there were some smaller ones also that are missing as well. But we do have fin spines. There are fin spines, like I said, all 4 of these kinds. This is a fin spine. Looks pretty fragmentary, and it is. But we had this identified by a shark fossil expert, and he said that's definitely a fin spine from a shark. And he calls it Tenacanthus, with a question mark. Could be a different kind of shark, but probably Tenacanthus. The third of the 4th kind of fish were the Acanthodians, or spiny sharks. And we had spines from those sharks too. This is what they look like. They're called spiny sharks for a good reason. They had all kinds of spines, not just fin spines, but also all these spines down here. I should probably hold this hand more. And they were definitely spiny. They were bony. They had bones. They weren't bony fish exactly as Osteichthyes, but they were starting to kind of get that way because they had more bones than the arthrodires did. But their most characteristic thing are all the spines all over them. And here are a couple of pieces of spine, nothing impressive again. One of these is in the Smithsonian, one is in the Harvard Museum of Comparative Zoology. Then we get the Osteichthyes, which is the rest of them. Most of the fish that we know of are the Osteichthyes, the bony fish. Most of your game fish are Osteichthyes. The aquarium fish are Osteichthyes. And they have bones, bony skeletons, endoskeletons. And there were 2 different kinds. There were the actinopterygians, which are most of the game fish, rayfin fish, and the sarcopterygians. We didn't have any rayfin fish here, but we did have sarcopterygians. And these are the things that probably evolved into the amphibians. The lobefin fish. And you can see here, that probably is what evolved into our legs, our arms rather eventually, and that is eventually what evolved into our legs. We don't have any arms and legs here, but we do have a few bones and lots and lots of teeth. Actual teeth, not just tooth-like structures like the placoderms had, but real teeth. They look like teeth. In fact, I used to be a dental lab tech, and I've seen a lot of teeth in my time, and these are definitely teeth. And they have lots of enamel, they have lots of pulp chamber, and they even sometimes have pulp. This is the one I was talking about earlier. It actually has carbonized pulp in its pulp chamber right here. I've talked to other people about that. They've never seen that before in a fossil fish tooth this old. Okay, so those are pretty much all the fossils that we have of the vertebrates. Now we get to another, and of all the animals, in fact, that's the end of that kingdom. Now we have our 3rd kingdom, the fungi. Not much here, but they were big. Like I said, these were in the early Devonian. This kind called Prototaxites was the largest organism on Earth. Imagine a mushroom the size of a house. And in the middle Devonian, when these were around, this is a little bit later than the early Devonian. By that time, that little amount of time, trees had come around. And so they were no longer the tallest organism on Earth, but we had some of those here too. The land plants, 2 different kinds. There were 2 different kinds, both arboreous, both tree-like. Cladoxylopsids and the lycopods. Cladoxylopsids, if you've ever been to the Gilboa or heard of the Gilboa forests in New York, has anybody here ever heard of those? Oh, good, I saw somebody. You actually raised your hand. Anybody else ever heard of that? They're famous fossil find in upstate New York of these big, huge, cool-looking tree stumps that are really old. Again, that's the first forest, middle Devonian. Same age as these guys. Those turned out to be Cladoxylopsids. Well, we have them here in Milwaukee too. And that was never published before. We were the first ones to put that in the book. They don't look really much like a tree on this one here. The next one does, but this is the bark from one of them. And that tree I've been showing you with all the stings stuck to it, that's supposed to be a Cladoxylopsid log. But you can see this pattern here. It's a very characteristic pattern of these structures in the bark that tell us that we're dealing with the Cladoxylopsid. That's too detailed to go into right now. This next one looks a little bit more tree trunkish. I think it does. Probably most of you do too. It's about a foot wide, As you can see, that scale bar is 4 inches high, the cone parts, so it's like a foot wide. It's tree bark. Now, at first I thought this was actually, when I looked at this, before I sent these photographs to a plant specialist, a fossil plant specialist, Paul Kenrick, I thought that these things were lycopods because I had seen the lycopods before. They look kind of like this, and you've seen them. I heard somebody talk about the Peabody Coal Company today, and there are lycopods all over the place. In fact, the Pennsylvania, the Carboniferous period, which is the next one after the Devonian, that was it, the coal age. Most of that coal was made from these things, from lycopods. They were just starting out here right now, in the middle of one. This is the very first lycopods we had, but they still look like lycopods. This is a branch from one of them on the left here. It shows the little tiny leaves there on the sides, and all these little structures in the middle here are leaf scars where the leaves broke off. These are what the trees look like, roughly like that. It's a sketch. We also have more of these. By the way, the lycopods are still around today. If you've ever made a Christmas wreath, or seen any of Christmas wreaths, say that 5 times fast, Christmas wreaths, those are typically made out of lycopods. So of course, the lycopods today are shrubby little, but again, in the middle Devonian and the early Carboniferous, they were huge, they were tree-like. There were also some shrubby ones at the same time, but they had the big ones. So when we were first looking at these, we thought, how do we know that these aren't some of the shrubby ones? They could be, but they're lycopods. These could be just parts, major parts of these things. These cells are maybe 4, 5, 6 inches long here. But we know that we got lycopods here, guys, tree-like lycopods. Well, first, these are leaves that broke off. Because we got bark. And this bark is 10 inches wide right here. That's a tree we're dealing with again. With the typical lycopod leaf scars, just like Sigillaria, Lepidodendron from the Pennsylvania. Very similar, very reminiscent of that typical scale-like leaf scars. These are 3 views of the same piece of bark. I cropped them differently so they look different. But it's basically front, back, side view. So the lycopods. Tree-like, towering over everything else, along with the cladozylopsis. So much for that kingdom. Now we got, in fact, that's all 4 of them. That's all she wrote. The rest of these here are trace fossils, which are, we just got done dealing with what is a fossil. A fossil is the remains or traces of prehistoric life. We just got done talking about the remains. Now these are the traces. And not too many of these, but there's more than we ever thought. The ones on the left are worm burrows. Worm burrows. What the heck is that? There are so many phyla worms. We don't know what kind. But as I mentioned, we do know that there were annelid worms. We knew that there were scalicodonts, therefore there were annelid worms. And so this could be from them, maybe not. This one on the right is very interesting because these are worm burrows in a cephalopod. Almost all cephalopods, if you've noticed the pictures before, have worm burrows on them, which is very unusual. Some people have actually studied this and they're still studying this phenomenon. It's only seen, mostly only seen in the Milwaukee region, with few exceptions. And so these have names. It's Vermiformicnus on the left, Arthrophycus on the right, more worm burrows of different kinds. Burrowing, this one's associated with brachiopod, this one's just in the sediment, different kinds. So probably different behaviors from the same animal or different animals, we don't know. And they're probably worm-like. Okay, and there's another one called chondrites, same thing, different kind, probably different species making this type of a burrow. Then we get unidentified body fossils. Every formation of rock that has fossils has stuff you can identify. And these are some of the random ones that I picked out. I don't know what they are. The one on the right, I mentioned Lichenalia, might pop up again. This one on the right might be Lichenalia, but I've never seen a Lichenalia that looked like it was carbonized. It's bryozoan, carbonized, which you don't really get very often. But it might be just a weird, aberrant kind of a preservation of bryozoan. Could be. But these, I have no clue what these are. These are probably from some part of a plant, just because they're black, I don't know, I'm guessing. Maybe some kind of an animal. Your guess is as good as mine. looked almost like a wing at first, but anyway. So now we're just going to talk a little bit. This will not take long, guys. Fossil collecting in the Milwaukee Formation. There is none. Okay, not anymore. That's a gross exaggeration, but in a nutshell, that's kind of what the state of affairs is. This place here, there's fossils all over the place. That is Estabrook Park. That's the type locality of the Milwaukee Formation in Milwaukee. Kevin's been with me there many times. We found tons of fossils in this thing, but you can't keep them. They've now made a law where it's no longer legal to collect and keep fossils. You can't remove anything from a Milwaukee County park, which this is in. So, bye-bye. That's a type locality, so you would have to be very careful of it anyway, because that's the last place where you can go and find stratified rock, basically. All the rest of the stuff is on private property or it's inaccessible for one other reason. That's what the stuff on the right says up here. On the left, it talks about where you can find some stuff from the Milwaukee Formation. If you want to go up and down, look at all the weathered rocks along Lake Michigan, up and down, even down into Illinois, you'll find occasional things, but they're weathered. And you'll find also, if you want to go to a quarry in Milwaukee County or a construction site in Milwaukee County or in Waukesha County, you're probably going to find some Milwaukee Formation fossils in there too. But they've been kicked around, tumbled around by the glaciers for thousands of years, and they're not going to be really good either. So don't get your hopes too high, but you'll get something out of that. Maybe something will polish up nice. Some of the stuff is silicified and will look nice that way. And you can sometimes identify some of these things, but usually you can't even identify them. It's a species. That's a sad thing, but there's hope because there are major collections where you can still see these fossils. You can go and study them if you really want to, and some of them are actually on display. So probably the largest collection that is on display is located at the Green Gallery at UWM in Latham Hall. But most of the Green's extensive collection is kept in compactors away from public view. The collections of Charles Monroe, Gilbert Roche, Joseph M. Liddy, and other collectors are maintained at the Milwaukee Public Museum, which is a gigantic collection of collections. But again, most of this material is not on display. The massive private collection of businessman Edgar Teller, who used to pay the quarry workers, who was one of the guys who paid quarry workers to find stuff for him in the heyday when he made cement. And he's just tremendous collection. Has been split up between the Smithsonian, the Field Museum, the Royal Ontario Museum, and the Buffalo Museum of Science. And the Fisk Holbrook Day collection is located at the Museum of Comparative Zoology at Harvard. And also the collection of Herdman Cleland, who wrote the 1911 book that I referred to, resides at Williams College in Massachusetts. So there are places you can go to see these things on display. There's even a couple of them, at least one that I know of that's on display here in this museum. But typically, because the Devonian was so, as I showed you in that very first figure, so limited, only Milwaukee. There's nowhere else you can go other than the Milwaukee area to get that stuff. You have to go all the way to Iowa, across the border into Iowa, and into that before you find anything like this. And some of the species are the same, but they're still very different. And that's not nearly as diverse as this. Okay, Earl, nearing the end. Here are photographs of a couple of the museums. Figure A shows the original Thomas A. Green Memorial Museum at UWM. B shows where the large Green collection is now located, because it was pulled out of there and they lost their National Historic Landmark status as a result of that. But they put it now in the basement of Latham Hall, and which is actually probably a better thing. I hate to say it because I really hate to see it leave the museum, but they're in the compactors now. They're in the basement, so if there's a fire and there's a flood down there, we got some problems. But they're in pretty good shape now, and they're being curated pretty well. And also, also the figure C shows where most of the Devonian material is located at the Milwaukee Public Museum. So these are the collectors that collected all the fossils that I showed you in this presentation. And these are people that are responsible for some of the images that I showed. So we now have a pretty good picture of what Milwaukee looked like about 385 million years ago. This painting by Richard Bisley, based on fossils from the Milwaukee Formation, shows some of the richness and diversity of its life. A lot more work still needs to be done on the biota of the Milwaukee Formation, and we encourage researchers to prepare and study the thousands of fossils held in museums in Milwaukee and around the country for what else it will teach us about the wonderful world around us. I thank you so much for your attention.